AI assistants are everywhere, but have you ever wondered what's actually going on inside one of these models? Well, today we're going to find out, and we're going to do it entirely in Excel. What you're seeing here is actually a Micro GPT model running live in a spreadsheet, and every single calculation is visible and inspectable right in this spreadsheet. It's a tiny model rather than an all-knowing AI assistant, and is only trained to generate plausible sounding names. But when we hit recalculate, the entire model runs and generates a new name. So it's a real generative AI model. It's just very, very small, but it's written entirely in Excel formulas, making it really easy for us to trace exactly what's going on inside. Now, I've made the spreadsheet available for you to download. I'll put the link in the description so you can follow along and try it for yourself. If you've seen my other videos, you'll know that I usually talk about Pixel, an Excel add-in that lets you call Python functions directly in Excel. So it might come as a bit of a surprise that today I'm just going to be doing this entirely in Excel without any Python code at all. Now, earlier this year, Andrej Karpathy, one of the original researchers behind GPT, released an incredibly short implementation of a GPT algorithm called Micro GPT. And at just 200 lines of Python with no dependencies, it really distills the essence of a GPT model into an easy to follow program. So the obvious thing for me to do would have been to take that script and just embed it into Excel using Pixel. And that would have been, really easy to do, and it would have actually been kind of a great use of Pixel in practice. But I thought, what about instead of doing that, instead of hiding the Python code behind an Excel function call, we took the Python script and unrolled the whole thing into Excel formulas. And that way we can kind of really see exactly what's going on through the model, and anyone without any Python knowledge can open the spreadsheet, click on any cell and inspect what's going on at each step. And that's the spreadsheet that I'm going to be showing you in this video. So there are 3 sheets in this workbook, and we'll start with the parameters sheet. And this is where the model stores everything it's learned. You can kind of think of this as the model's memory. It's a big collection of numbers organized into tables, with each one playing a specific role in making predictions. When you hear people talking about the number of parameters a model have, this is exactly what those parameters are. And we've got a matrix of token embeddings, position embeddings, attention weights, and projection matrices. And we'll come back to what each of those mean as we work through the model. But the important thing to understand for now is that these parameters are the result of training the model, and they encode how the model has learned to behave. In total, this model has just over 4,000 parameters, and that's just 4,000 numbers that together define everything the model knows. To put that into perspective, GPT-3 had 175 billion parameters, and GPT-4 and newer models are much, much larger. So the model that we're looking at here is genuinely just a little toy, but the structure is very, very similar, and the same ideas that are in this spreadsheet are in every large language model that you're using today. They're just applied at a much, much bigger scale. Before we get into the model itself, I want to take a quick look at this function sheet. In here I've defined a few helper functions using Excel's Lambda feature, and you can see them here. We've got linear, softmax, RMS norm and sample, and these are the sort of mathematical building blocks that the model uses at each step. In the Python code, these are just 1 or 2 lines long, but here we've used Lambda to make them Excel formulas, but they do exactly the same thing. And this is actually a great example of where Pixel can shine, if you wanted to use that. You could replace any of these Lambda functions with a Python implementation and then call that directly from Excel as a normal worksheet function. But for this demo, everything stays in pure Excel, so we've implemented them using Lambda. Okay, so let's get into the model sheet, and this is kind of where everything happens. And at the top you can see we've got a few controls. There's the starting character, the temperature, and then the output. And then below that we've got the entire model computation flowing downwards 1 step at a time. Now, the model doesn't work with letters or words directly. Instead it works with what it calls tokens, and tokens are just numbers. And the model's job at each step is to take the tokens it's seen so far and then predict the next one. Now in our case, tokens map 1-to-1 onto characters, so token 1 might be A, token 2 might be B, and so on. And you can see the token IDs here, and next to them there's the characters that they correspond to. The model generates the next token. We look up what that character maps to, and then that becomes the next letter of the name. And we repeat that until we hit this special end of name token, and then that's the model done. Now, a token ID like 1 doesn't carry any meaning on its own, so the first real job of the model is to turn each token ID into something richer, and in our case that's going to be a list of 16 numbers called an embedding. We've got two of these here. We've got the token embedding, which looks up a row from the WTE table in the parameters, and it's basically asking, what does the model know about this particular character? Next we've got the position embedding, which does the same thing from the WPE table, but for the position in the sequence. So it encodes whether we're looking at the first character, the second character, the third, and so on. Then we add these two embeddings together to get what's called the joint embedding, and that's a single vector that represents what the character is and where it is in the sequence. Then we pass it through the RMS norm function, and this just rescales the numbers to keep them kind of well behaved as they flow through the network. You can think of it as tidying up, so there's no single number that dominates. The next block of the model is the attention mechanism, and this is kind of the heart of the transformer, and it's the idea that was made famous in the paper titled "Attention is all you need." The idea is kind of relatively simple, and it's that when we predict the next character, not all of the previous characters are equally useful. So if you've seen S, A, M, E so far, the model should probably pay more attention to certain earlier characters depending on context, and the attention mechanism is how the model figures out what to focus on. And here's how it works. For each position, the model produces three things from the embeddings. It produces a query, a key, and a value. Now the way to think of the query is like a search query, sort of asking what kind of information am I looking for right now? And each previous position has a key, which describes what information it holds, kind of like a label on a filing cabinet. The model then compares the current query against every key it's seen so far, including the current one, to produce attention scores. These scores are then turned into probabilities using the softmax function, which takes any set of numbers and squashes them into values between 0 and 1 that sum to 1. So these attention scores then become weights, and they say, how much should I draw from each previous position? And that's where the value comes in. So if the key is the label on the filing cabinet, the value is what's actually inside it. That's the content the model reads out and carries forwards, weighted by how relevant that position turned out to be. Now, rather than doing that all in one big space, the embedding is split into 4 separate subspaces, and we run attention independently on each one. In our model, we have 4 attention heads, and those are broken down into 4 blocks in the sheet. The idea is that each head can specialize. So one might learn to track which vowels have appeared, another might track position patterns, and so on. Each head works in a smaller focus space, which tends to work better than one head trying to do everything at once. And afterwards, the outputs of all 4 heads are concatenated back together and projected down to the original embedding size. After attention, the result passes through a small neural network called the MLP block, and that's short for multi-layer perceptron. This expands the embedding from 16 numbers up to 64, so 4 times the original size, and then applies a rectified linear unit activation function, which just means that any negative values get set to 0, and then it projects the result back down to the original length of 16 numbers. This gives the model some extra capacity to transform the information it's gathered from attention. So this expansion and projection are done using the matrices that we saw on the parameter sheet, and those, along with the attention weights and other parameters, are what's learned during training. So next, kind of crucially, we add the result back to what we had before, and that's what's called a residual connection. And it's kind of a trick that helps the model train better. It means information can flow directly through without being transformed, and the network only learns the difference between that baseline. So the result from the MLP block and actually the attention block uses the same thing. Those both produce a delta, which is then added to the input number to produce the final result. Now, in the last step, we take the output of the transformer layer and project it back to the size of the vocabulary. That's our 26 letters, and there's one number per possible next character, and these are called logits. So just like with the attention scores, we pass these through the softmax function to turn them into a probability distribution. So that's the model saying, given everything I've seen so far, here's how likely each possible next character is. We then take a random sample using that probability distribution to pick the next token. And that's why the output is different each time you hit recalculate. Then the whole thing repeats. The predicted token becomes the input to the next step, building up the name one character at a time. The temperature control at the top of this sheet feeds directly into this step. A lower temperature makes the model more confident, it pushes probability towards the most likely character, and a higher temperature spreads the probability more evenly, making it more random and creative, so we can see that in action. Right now the temperature is set to 0.5, which is fairly conservative, and if I press F9 a few times we can see the output changing, but if I now push the temperature up nearer to 1 and then press F9, we can see that the output gets a little bit more weird. And if I drop it right back down to say 0.1 and then recalculate a few times, so it tends to converge on the same thing every time. So the model is then just picking the single most likely character at each step over and over. And there we have it. That's the whole model right there in a single spreadsheet. And you can have a look in any cell and you can see exactly what's calculated at any stage. So we've talked a lot about the model, projecting and expanding embeddings, but what does that actually mean? So embeddings are just a list of 16 numbers, and that's all. And there's one embedding for each possible token, and those are in the WTE block, and there's one for each position in the WPE block. And the model just picks out the right one for the current token and position. You then take the joint embedding, which is just a list of 16 numbers, and multiply it by the attention WQ matrix to get the query, or you multiply it by the attention WK to get the key, and the same for the attention WV to get the value. Similarly, the projections in the MLP block are matrix multiplications as well, and they're just the MLP FC1 and FC2 matrices. Finally, the output of the MLP is transformed by the LM head matrix. But the important thing to realise in all of this is that these parameters that make up the various matrices are all learned at training time, and that's kind of the really clever part. So for some real sample data, in our case a list of actual names, we compute a measure of the error between what the model produces and what our real value is. And then we tweak all of these parameters to try and minimise that error. So just like in Excel, where we might use goal-seek to search for an input value that gives the right output value for a formula, here we're doing a similar thing, but instead of just tweaking one number, we're tweaking a few thousand numbers, or in the case of a real model, we're tweaking a few billion. So if you want to know more about how the training kind of actually works, leave a comment on this video and like the video, and if there's a lot of interest, I'll put that together. So there you have it, a working GPT model built entirely in Excel, and we've seen tokens, embeddings, multi-head attention, the MLP block and sampling, all laid out step by step, one row at a time. And it may only be a simple model, but it's a fairly complex spreadsheet, and I would never really advocate building this much complexity into an Excel sheet in this way for anything other than a learning exercise. Instead, I'd much rather break the model into high-level functions and write them in Python, where they can be more easily debugged and tested, and then expose those high-level functions to Excel using Pixel. And if you want to know more about calling Python models like this directly from Excel, check out Pixel at pyxll.com, and feel free to drop me a message with any questions. So I hope you found this video interesting. Please do give the video a like and subscribe to the YouTube channel. It really does help. And I'll see you in the next one. Thanks.